Hey class, I wanted to do this last video over linear systems, even though this is a little late for this particular video. Next time there's a class, you'll have it early. So here we're looking at systems. Okay, so the general form is going to be like this: x prime equals a x, but now where this is a vector of derivatives, and so this is a vector of the functions we're trying to find, right? And this is a matrix. And in this case, the only thing I'm going to discuss is where the matrix are all just scalars, right? So just elements of R, maybe just elements of the complex numbers, but in this case, just elements of R. So writing this out in a little like 2x2 system, it may look like this. It may look like x1 prime, x2 prime. These would be functions of some variable t, say. Right, so that's our vector of derivatives, right? Would be equal to some vector matrices. I'll just make something up: 2, 3, 1, 4, right? So there's a matrix. And then I have here x1 of t, x2 of t. Okay. And in this case, we could write this like x1 prime of t is equal to 2x1 of t plus 3x2 of t. That's what we get from this matrix vector multiplication. And x2 prime of t, looks like a 1, is equal to 1 x1 of t, so just x1 of t, plus 4 x2 of t. Oops, x2 of t, like that. That's not there. Okay, so that looks like a normal, system, right? And then this is usually given with a couple of initial conditions, like, and I guess there's actually a couple of options here, but in this case, I'm just going to consider the case where we're giving x1 of 0, x2 of 0 as an initial condition. Okay. So there's a couple of ways of thinking about this. I'm going to think about this very linear algebraically in a way that, in my mind, works anyway, where you really don't have to do any work in some sense, right? You know exactly what the answer is, but actually sort of figuring out then what the answer is, right, takes a little bit of work. But how to solve it doesn't take any work. So here's what I'm going to do. Okay. Now there's kind of a little bit of magic here. So I guess in some sense what I'm going to tell you is just true, right? And working through the exact reasons this particular thing is true would take us too far afield. But I've got this, I'll put a little like an arrow over there to indicate this really is a vector, right? Equals ax, right? This is really just like our single first order system. This, I'll just put an ax here, right? And in this case, we know the solution is x equals what? E to the at times the, some constant. And actually that constant would be the initial value of x, right? So x naught. All right, so we know the solution for that. That was like one of the first kinds of differential equations we looked at. And I guess literally we use separation of variables to get there, but there's other ways to attack that. I'm going to claim that the same is true here. Given this, so x prime equals a x, all right, the solution is simply x, the vector of functions, is equal e to the a t x at the initial values, right? So very same solution. So that's what I mean by no thought, right? So no thought involved here. The only thing is now we have this question: what is e to the matrix? So like in the case I had up here, right? This very simple case where I have the matrix is 2, 3, 1, 4, right? This would look like this. This would be saying that the solution is x1 of t, x2 of t is equal to e to the matrix. Sorry, not my memory isn't that good. 2, 3, 1, 4. 2, 3, 1, 4 t, right? And then the initial values, which is just the vector x1, 0, x2, 0. So what in the world is that thing, right? Well, it's something to a matrix, so we might think, well, whatever it is, it should probably be a matrix. And that's true. And so here's the reasoning. Now this will go just a little bit in this. So what I'm going to do now, we'll go a little bit into the math as to why this statement right here is actually true. To really verify this statement, we would need to talk about what derivatives in n-dimensional spaces are and stuff, right? So there's and we would have this operation which is going from an n-dimensional space. Anyway, there's stuff there we're not going to do here. But this is a little bit of that. So what is e to the at? Or in general, in fact, let's just forget what e to the at is. Let's just say what is e to the b for something else, right? There's a few ways you can define this, but one is like this, and the useful one for us is like this. It's this infinite series, b to the n over n factorial, okay? And one thing that maybe you remember, is that this thing converges for all values of b, right? And then it has properties. We can do things like we can take this thing, right, and raise it to a power and see that it behaves like it ought to. We can take like e to the b time, let's see, e to the b plus c, we put b plus c in here and see that it requires some work, right? But see that it behaves like exponent should behave there. We can take the derivative of this thing. That's actually easy to do, right? So pretend this is a variable for a second. So let's take d db, go both sides, e to the b, right? Because maybe this is really probably the most important and easy to see. I equals 0 to infinity, b to the n. Well, okay, and then there's a little bit of something here I have to do that would need to be justified in a analysis class. So let's be, I could bring this derivative in, right? That actually needs to be verified, right? But when I do that, I take this thing, so now I get summation I equals 0 to infinity. This becomes nb to the n minus 1 over n factorial. But then I have an n here, n factorial there, so this is just summation. I keep saying n on this side and I on that side, which is just dumb. I'll just change these to n. All right, these should all be n. That should be n. Okay, so n equals 0 to infinity, right? And then what I'm going to have here will be b n minus 1 over n minus 1 factorial. Because when I cancel out that, I get n minus 1 factorial. And actually, I lose the first term because, so this is not literally correct, because the first term here is going to be 0, right? Because the b to the 0, this is going to become 0, right? So the first term is just a constant term, so it goes away. So what I really have here isn't this. I really have this, right? And then what I can do is just play with the indices, right? When you play with the indices, I just rewrite this. If I subtract 1 here, I subtract 1 there, so I get n equals 0 to infinity b to the n over n factorial. And what do you know? That's e to the b again, right? Because it's the same expression as what we started with. Sorry, right there, right? So I take the derivative of that, and I get back that again, right? Anyway, the same same reasoning works with matrices. Once you understand what the right notion of derivative is there. And so in particular, we're going to define e to the a equals summation I equals 0 to infinity 1 over n factorial a to the n. And now it's like, well, how does that help? I mean, how do I, these are like, powers of matrices. That's a complicated thing to do. It still doesn't really tell me what a solution is. That's true. So now here's where the real sort of linear algebra kicks in. So this, up to here, this is all kind of analysis. It's not really linear algebra yet. The next step is we're going to take A and diagonalize it. So what that means, we're going to write A is equal to S d S inverse, right, for some invertible matrix S, right? Sorry. And so, so in this case, I'll just stick to this kind of 2 by 2 case, right? So, and it doesn't really matter if I spell out what A is. I'll just leave A, but it means that I'm going to have, so let me just be a little bit careful. This is, well, okay, let me just, let's do it in general first, and I'll drop down for a simple case. So if this is n by n, right? All of these are n by n. This is n by n. This is n by n. Okay, these are both invertible. I mean, well, this is invertible because this inverse is there, right? This is n by n, and it's diagonal. So d is equal to I'm going to write this maybe suggestively lambda 1 through lambda n. Okay, and we'll see in just a minute that these have to be the eigenvalues for A, right? And then so that means this S here would be V1 through Vn, like that. These are column vectors, right? Because it's an n by n, so each one of these Vi would be an element of, say, Rn. Okay. And so if we sort of think about what this says up here, this says SD equals AS. Okay, now I'm going to think a little bit about our matrix multiplication. This is V1 through Vn, lambda 1, dot, 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 lambda n equals, and over here, I'm going to have just A and then V1 through Vn, okay? And then I'm going to think about these two different ways of multiplying these things. So here I'm going to think about doing this sort of, how do I say this, kind of multiplying the columns by the rows here in some sense. But I'm multiplying, sorry, how do I want to say this? How do I want to say this? Okay, sorry, I got myself confused actually. Actually, I'm going to do the same calculation. So I'm going to take this thing and multiply it through here, right? When I take this matrix and multiply by this first column here, what it's going to do is take lambda 1 of the V1s and none of the others, right? Add it together, right? So I'm going to build this thing one column at a time, right? And so what I'm going to get in the end is I'm going to get lambda 1 V1, up here, so lambda n Vn, right? Same thing on this side. I bring a in, so I'll get AV1 through AVN, right? So this will be AV1, AVN. So I'm building these two products by building the product a column at a time by taking the matrix on the left in each case and multiplying it through the matrix on the right, column-wise, right, like that. And so I build these in columns. But notice that what I get here as I get looking across here is I get the AVI equals lambda IVI, right? So in particular, what I'm saying here is I must have, so it says that this is an eigenvalue eigenvector pair. And since S was invertible, what this is saying is that this must be a basis of eigenvectors, right? And the diagonal elements here are exactly the eigenvalues of A, right? And then the ith column of this S is just the eigenvector, well, an eigenvector corresponding to the ith eigenvalue, right? So this really is about diagonalization in some sense, okay? I mean, it's really about the eigenvalue eigenvector stuff, right? But when we have this kind of relationship, we say that A is diagonalizable and D is a diagonalization of A, okay? The S's are not unique because I can always choose different eigenvectors, but the eigenvalues are unique up to the order in which they occur, right? We could reorder these, right? So that would make slightly different versions of this. We'd always have the same A. I mean, A is a fixed matrix, right? So with all that said, right, so let's suppose A is diagonalizable. And I'm trying to compute this funny e to the a thing. So this is summation I equals 0 to infinity, 1 over n factorial, a to the n. So here's a really nice thing about diagonalizable matrices, right? If a is equal to s d s inverse, right, then a to the n. So what is this? Well, it's s d s inverse, s d s inverse a bunch of times, right? S d s inverse. But these cancel out in pairs, right? So this is really just 1s d to the n s inverse, right? So we don't have to worry about all those s's. And the really nice thing is when d is diagonal, right? So in this case, d is lambda 1 through, lambda n, everything else is just zeros, right? Then d to the n, so when I take diagonal matrices and multiply them, I just multiply the diagonal elements. So if I take a power, I just take the power on the diagonal elements. So this is just lambda 1 to the n through lambda. Sorry, I shouldn't do the n because I've got n there. Sorry, bad me. Let's say m, just to not have the same letter showing up in both places. M, right? So, so taking the power of a diagonal matrix is really easy. Taking the power of an arbitrary matrix is really hard, right? I mean, it gets very complicated, huge numbers, and all sorts of problems, right? But taking the power of a diagonal matrix is trivial. You just take the power of the diagonal entries, right? So that's the magic here, right? So what happens with this when I do this, right? So e to the a is really e to the s d s inverse, right? So that is summation I equals 0 to infinity, 1 over n factorial s ds inverse to the, I have to keep using wrong, so I've got n in use. Let me just go back to I. Sorry about, there's too many letters around. To the I, I'll try to stick with I here. Okay, because right now I'm saying n is the dimension of these spaces. Right, but we just saw that this is I equals 0 to infinity, 1 over I factorial. I can pull the s out, move the d in like that, s inverse like that. Now I can just, this is a sum over a product, so I can pull the s's out on both sides, right? And so then I actually get e equals to s summation I equals 0 to infinity, d to the I, s inverse, right? But this is now a summation over diagonal matrices, right? So this is now just s. And then if we sort of jump inside here, we look at the summation. This is summation I equals 0 to infinity, lambda 1 to the I. And then all the way down, summation I equals 0 to infinity, lambda n to the I. And then s inverse, right? But what are these? Well, this is just e to the lambda 1, e to the lambda n, right? So this is just s, e to the lambda 1, dot, 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 e to the lambda n, s inverse, right? So this is really cool because if A is diagonalizable, right? I mean, I guess the upshot of this in some sense is that the, e to the d for a diagonal matrix. So let me just keep it small. So e to the lambda 1 through lambda n is literally just the matrix e to the lambda 1 through e to the lambda n. So diagonal matrices are really amazing because they behave a lot like just numbers. So I want to exponentiate a diagonal matrix. I just exponentiate each diagonal entry. Amazingly simple, right? And then so the e to the a is like that, right? So now going back to our system, right? I have x prime equals ax. That's a given. That's my equation. I've got x of 0. That's given as initial values, right? Whatever they are. The solution is e to the a t, and then the initial values that were there. So this is my solution. So again, essentially no work in some sense, right? Okay, now I diagonalize A, so I get E. Now you can't diagonalize all matrices, so I'm making an assumption that A is diagonalizable for this part, right? And then I get x bar equals, based on what we just saw, S e to the dt. This is a diagonal matrix, right? With just the eigenvalues down the middle. I mean, it's a little different than we had before because we're multiplying by t, but that just means the diagonal entries here are lambda 1t, right? Lambda it, right? S inverse, right? And then times x naught, right? So there we go. Okay. So what is this guy here, right? So again, this is, e to the lambda 1t dot, 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 e to the, sorry, let me think for a second. Nope, yep, this is exactly what I say. E to the lambda nt, right? Oh, sorry, lambda nt, right? I'm just multiplying by t right now. Okay. And we just showed that when we do this exponentiation, right, it just turns out to be the matrix e to the lambda 1t down through e to the lambda nt. Okay. So this is awesome. We're almost done here, right? So after all that work, so where's the hard work in some sense? The hard work is you have to diagonalize a matrix, right? So right now I'm just sort of saying you have to do that. And once it's done, everything is easy, right? So if I write this out fully, so let's go back to the case where I just have two. So I have x1 of t, x2 of t, right? when I have my matrix. And suppose I've diagonalized it, right? Then what I have here is I have my two eigenvectors, v1, v2, for lambda 1, lambda 2. That's this S. This is S, right? And I have e to this thing, so I have now this matrix is just e to the lambda 1t, e to the lambda 2t. Nothing special about 2. It's just easier to write than all these n's, right? And then I have this other part out here, which I'll just keep writing as S inverse of x naught, right? So I have that part. Okay. We'll actually have two things you can do with that bit out there, right? So let me just sort of suppose that we do this calculation. So I'll think of this in two different ways. So we do this calculation. This is a 4x4 matrix times a 2x1 times a vector, right? So the answer is a vector. So let's just suppose it's C naught, C1, right? So we have S, so we can calculate S inverse, and we have the initial value, so we can just calculate this, right? We just calculate it in MATLAB or something, whatever you're using. Then this system up here becomes like this. So I'll just do this in a couple steps. When I do this multiplication here, what I get is E lambda. Let's see. How do I really want to do this? Yeah, let's do it in these two steps. So when I do this multiplication here, I get yeah, right. So I get E in the first column. I get E lambda 1t v1. This is still a vector, right? And I get E lambda 2t v2. Right, and then I have this multiplication by this thing, which I'm just calling C naught C1. All right, and so when I'm done, right, I get this. I get this column vector right here is just equal to C naught E lambda 1t. I shouldn't call these, and I make this mistake all the time. Let me call these C1 and C2 just to match up. So let's call this C1 and C2. C1 and C2, so I'll call this C1, E lambda 1t v1 plus C2 E lambda 2t v2. Right, and essentially we're done now, right? So I could write this thing out. If I knew what these lambda 1s were, right? So if I knew that v1 is equal to AB, right, and v2 is equal to CD. So we've computed these things, whatever they are. Then what I actually have here is I have that here I'll write it this way one last time, and then I'll write it out as a system. So x1t, x2t equals c1 e lambda 1t, and then times this first vector, which is this ab, right, plus c2 e lambda 2t times this vector cd. Okay, and then we can write it as a system x1 of t equals C1 C1. I may as well bring the A over here. C1 times A e to the lambda 1t plus C2 times C. Maybe C is a bad letter there, but e lambda 2t, right? Then x2 of t will be C1 times B e lambda 1t plus C2 times d e lambda 2t, right? So we've essentially satisfied our system. Now here's one little thing when you're actually doing a problem. So there's two ways to deal with these C1, C2. So one is to just calculate it. Where did I have this? Yeah, here, right? We know S, so we know S inverse, so we can just calculate this thing, right? That's one option. Another option would be to plug in 0 here, right? And so leave C1 and C2 as kind of variables that we don't know yet, right? And then we would get here a system, which would be x1 of 0, x2 of 0. So we could just solve here, right? When we put in zeros here, these all become 1, all these e to the something, right? So then I end up with A C1 plus C C2, and here I end up with B C1 plus D C2, right? And then we could solve that linear system. Of course, if we write this out as a matrix, this just says that A, B, C, D, C1, C2 equals x1, 0, x2, 0, right? But this is just S, right? So really when we solve it, we get exactly what we had before, that C1, C2 is equal to S inverse of X1 naught, X2 naught. So there's no benefit, right, in sort of saving this to solve at the end. We already had S, so we already had S inverse, so we could have just done that there. Same thing. Anyway, that is the method, okay? And then there's, and so I go through this twice in the notes, and then I go through an extra example. And now sometimes doing examples actually get harder than the method itself, right? So what I did for an example is I took a previous example, which was just second order linear with constant coefficients example that we solved earlier in one way, right? And we can always take these sort of things and turn them into systems by taking, in this case, I take y1 and call it y1 prime and take y2 and just set it to y. And so I get this system here, which is equivalent to that system up there. And the initial value, these two initial values become those initial values, right? So now I've turned this into a system of first order equations. Very standard technique, okay? And then now I'm doing the diagonalization, right? So to do the diagonalization, I have to find the eigenvalues. These turn out to be complex. We know from the previous example this is a spring, so that's not surprising because we have oscillating motion. Then we find the eigenvectors, right? Go through here and find all the eigenvectors. I'm not sure what that S is. I need to fix that. So here's our A all sort of diagonalized out. There's S, there's the eigenvalues, there's S inverse, right? Here's S inverse computed, right? And then here's S inverse Y naught. So that's like the thing I was calling C naught, C1, C2 is like right here. Those are those things. So the numbers get messy, right? But it's all just sort of calculation at this point. And here's the, we get a final answer down here, right? So that's kind of nice, right? So that's how that works. Good. All right. Yeah, I thought I wrote this final answer as just sines and cosines. So maybe I should. Oh, I see. Yeah, no, I see. We've already done it above, right? So I indicate how to do that before. So turns out there's only a real part. I mean, there's lots of complex numbers here, but this is actually a real function. That was done earlier. We did all that math before. And then I give you another example, which is fun. So now I have 2 masses and 3 springs. So this gets really complicated. But the method is exactly the same. So this gives me, I've got 2 springs. So I've got 2 spring systems. So I've got 2 second order linear equations with now 2 different variables over here, right? So I get that sort of system. And as I did before, we can turn this into a 4x4 system of first order equations. Anyway, the solution's pretty long and messy, so I put that in a separate sheet you can click in and look at. I did all the work here, all sort of by hand. I did use MATLAB to verify everything I was doing because it's real super easy to make lots of mistakes. There's lots of math going on here, right? And then I gave you this little thing you can click on and you can play with it actually, which is kind of fun. So if we blow this up, you can just, so here I've got, I've set my X1 and X2, the way those springs are sort of stretched down. So pretend this is like the left wall and right walls, right? So each are stretched. And then you can just slide this along and see how the 2 strings, the 2 masses would move relative to each other. Or you can push this button and it'll just run and you can see how these 2. So you have to pretend there's some springs there stretching along the way, right? But there it is sort of in action. It's always kind of fun to animate our differential equations. Anyway, okay, so that is about 30 minutes, and so this is about to quit anyway, so that's a good stopping point. So that'll be the last video for this section.